Hello and welcome again. So now it's time we talk about another cipher, and in this case we're gonna talk about the DES or DES cipher. Now this video is just an introduction to this cipher, so we'll talk about a little bit of history of the cipher because it's a very interesting history, and also some of the properties we'll talk about in the class later that we're gonna introduce for this cipher. So first of all, what is DES? DES stands for Data Encryption Standard. And as the name says, it's a standard, and this standard was actually requested by the US government, and it was a private company who created this cipher. Now, the DES is a block cipher, and if you remember what a block cipher is, it's gonna take blocks of data, blocks of bits, and encrypts that block at a time. So the general picture here of the DES goes like this. So here inside this box, imagine that you have some kind of algorithm, like in the case we saw for the stream cipher. In here there was a random number generator and a sort gate. In this case, the DES or the DES is going to be a little bit more complicated than that. Actually, it's a lot more complicated than the stream cipher. So there's gonna be some encryption algorithm going on here. So what it does is something like this. So you take, in general, this is a very big picture, very general picture of what the DES does. It takes plain text, 64 bits at a time. So this is the block. So this cipher here acts on blocks of 64 bits, and of course it's gonna output 64 bits. So 64 bits of plain text are going to be transformed into 64 bits of ciphertext. And it's going to use a key here of 56 bits. So in this case, we're going to use just bits in this case. So that's in general what the cipher is going to do. This is just a block cipher. And then remember, all the block ciphers that we're talking about here are all symmetric cipher. So the process of encryption, which uses this key, is gonna use the same key for decryption. So the process of encryption-decryption will use exactly the same key. So in this case, X is the plain text, Y is the ciphertext, this one, and the key is gonna be just 56 bits. Now, of course, the plain text, if it is a longer text, it has to be divided into blocks of 64, and we'll talk about what happens when this ciphertext is not a multiple of this block. Okay, so as I said, it was created by a private company, and the data encryption standard was created by cryptographers at IBM in the 70s. Now, this was not the original name of the cipher. When the IBM created the cipher, it was not called DES. This was the name that was given by the US government once it was created, the cipher. Now what happens here in history is the NBS, which is the US National Bureau of Standards, requested proposals for a standardized cipher in the US. So basically what they did is they made a request to all companies in the US or people who were interested in making ciphers, and they collected all the ciphers that were submitted, and then decide which one was the one that they wanted to implement or they wanted to standardize. And the reason they wanted to standardize is because there was a need for encryption in commercial applications, for example, in banking. Now, several people or companies submitted proposals to the NBS, which is now called something different. It's not called the NBS anymore. So several proposals were submitted to the NBS, and the IBM's proposal was the one selected. Now, when the IBM proposed that cipher, it was not called DES, of course. So it was called something else. Now, also, once the proposal was accepted from the IBM, this agency, the NBS, requested help from the NSA, which is the National Security Agency, to investigate the security of the DES. Now, what happens is that, as the story says, the NSA actually change a little bit what the DES, the structure of the DES. So they change a little bit the key size. So for example, here in this picture, the key size is 56 bits. The original design that was submitted by the IBM, the key had a length of 128 bits. It was the NSA who decided to reduce the key size here for this algorithm. Why is the reason? We don't know. It's a decision of the NSA. Some people believe is because they wanted to introduce some kind of cracking or backdoor into the cipher so they can crack it easily, but there is no real proof that that was the reason why they reduced the key size. So that's pretty much the history of the DES. The ES is basically, it was created by the IBM by the request of the US government. The NSA was involved in the design, and it changed it after IBM submitted the cipher. Now, one important thing that we have to discuss here is, and it is very embedded into this cipher, is some primitive operations that achieve strong encryption. And this is basically, these two operations should be in any modern cipher. So one of those operations is called confusion. So what is confusion? Confusion is an operation that obscures the relation between the key and the ciphertext. And that's important because if there is some kind of relation between the ciphertext and the key, then an attacker could be with that relation. If there is some kind of relation, an attacker could maybe guess or crack the key, and that will be a problem. So we want to have confusion in our encryption algorithm. That usually happens when you do substitution. Now remember, we talked about this in the class, and usually the substitution cipher where you replace one letter by the other. In this case, substitution will mean replacing bits by bits, because now we're talking about data. The other important operation is called diffusion. Now diffusion is also very important. It's an important property that a modern cipher should have, and it goes like this. If you change one bit in the plain text, that change should change several bits in the ciphertext. Now it is really bad if one bit on the plain text will change only one bit in the ciphertext. So it means that the plain text and the ciphertext are somehow very closely related, and we don't want that. We don't want the plain text and the ciphertext to be as far apart as possible as we can. Now, this can be achieved by using a bit permutation. Let me give you an example where I mean by diffusion. Let's say, for example, we have a block cipher here, and that is a 8-bit cipher. Of course, there are no modern ciphers that are 8-bit. This is too small. But just for the example, let's just pretend here that we have a block cipher that is 8-bit. Now, I have two plain text here, x1, which is, of course, a sequence of zeros and ones, and x2 is another plain text, which is a sequence of zeros and ones. As you can see here, the difference between this plain text, or this byte here, and this one is only 1 bit, the 1 bit that I'm marking there with purple. There is only 1 bit difference. If this 8-bit cipher is to have diffusion, this bit change here in one position should change many positions in the corresponding ciphertext. Now this is x1 is the plain text, y1 is the ciphertext coming from the x1, y2 is the ciphertext coming from x2. So in the plain text, I have a 1-bit change, and you see here the green parts are the bits that are different from these two plain text, and you want that to happen. So I have a 1-bit difference here in my plain text, but that produces 5-bit difference in the ciphertext, and you want that to happen. You want the relation between the ciphertext and the plain text to be as far as possible, so the attacker doesn't have information, or doesn't have that much information to be able to crack your code. So in general, what you want to happen is 1 bit here should change approximately half of the bits in here in your ciphertext. So these are two important properties that a modern cipher should have. It should have confusion. no apparent relation between the key and the ciphertext, and it should have diffusion, which is this one. One bit change on the plain text should change several, and in general you want about half of them to be changed in the plain text. So that's two important properties there of the modern cipher. So as I said, modern ciphers use these two things, using confusion and diffusion. And what usually happens is they use a concatenation of those things. So for example, they start with the plain text, they do confusion, then diffusion, and then do it again, and do it again, and do it again by pairs. These kind of ciphers are called product ciphers because you do one followed by the other. That's why they're called like that. Now, another concept that we're going to talk about later, and this is because to get used to the language here in modern cryptography, is when you have a sequence of two operations, one confusion and one diffusion, you call that a round. And we're going to refer to this later because we're going to call things around. So what do I mean by that? So what I mean by that is this picture. Suppose I start with the plain text. And remember, modern ciphers should have diffusion and confusion. Most modern ciphers will actually do this. We'll start with the plain text. It will apply diffusion and then confusion. That pair there, this pair, the pair there, this is called one round. One round. And they will do it again. So they will do another diffusion, another confusion. So they will be diffusion 1, confusion 1, and then we'll do diffusion 2, confusion 2, and they will do several of them. So in general, they will do n rounds here. So n here denotes the number of rounds that you are gonna apply, and this is the nth round. So a modern cipher will have that concatenation of operation, diffusion, confusion, diffusion, confusion. And then finally, at the end, what you're going to end up with is your ciphertext, which is this one here, Y. Now, that's what's going to happen actually in the data encryption standard. What's going to happen is you're going to input here 64 bits in this algorithm. And there are going to be several rounds here. So what that means is it's going to be a diffusion, confusion, diffusion, confusion. And this DES is going to have 16 rounds. It means it's going to have diffusion, confusion, do it in pairs 16 times. And of course, it's going to output 60 bits of ciphertext. And the key is going to be 56 bits. So that's the whole introduction I want to talk about the data encryption standard. What we're gonna do in the next videos is gonna look exactly what's happening here in this box. So there's something going on in here that transformed this to 64 bits and of plain text into 64 bits of ciphertext. And what is going on here is a lot more complicated, as I mentioned, to what happens in the stream cipher. So there's gonna be a lot of operations going on here. That's gonna be operations that are gonna be performed on this 64 bits, on a block of 64 bits. So in the next videos, we'll discuss a little bit more about the inner structure or what the data encryption standard is. So I'll see you in the next video.